Howdy. This is my digital image processing for image, sorry. This is my digital image processing for ultrasound image ECEN333 final project. My name's Ruthie, and let's get into it. Here are the sections we'll be going over today. First section, description of the topic. So, what is digital image processing? Digital image processing refers to using computers to produce pixel image-based data. These systems typically take pixels as input and perform operations on that data and produce either improved images or extracted information. To understand this, we will start with how an image is defined mathematically. An image is defined as a two-dimensional function where x and y represent spatial coordinates and the function value represents the intensity or gray level at that point. This means an image Right. This means an image is not just a visual picture, but a structured set of numerical values arranged across space. Why is DIP important to biomedical engineering? DIP image processing is important because medical images are represented as digital data composed of these pixels. This allows computers to perform operations that improve image quality and extract useful information. Techniques such as noise reduction, contrast enhancement, and sharpening help to make important structures more visible. In addition, feature extraction methods such as edge detection and segmentation allow us to identify regions and boundaries within the image. General characteristics. So, there are a couple different tiers that we have for our specific characteristics. So with low level, there's image enhancement, which includes noise reduction and contrast, mid level, which has feature extraction, such as edges and regions, and then high level interpretation, which has image recognition and analysis. There's also a couple core capabilities that we have to include, like the quality of the image, the extractions of the structural features. And there's also some performance consideration like image quality, feature accuracy, and the processing efficiency or speed. So, some typical use cases for operating conditions of this project is that typical use cases of digital image processing can include diagnostic imaging, where internal structures of the body are visualized in real time. These systems are widely used to monitor and detect anatomical features. Ultrasound imaging operates under several important operating conditions. The data is acquired using transducers, which act as sensors that convert acoustic signals into electrical signals. These signals are often affected by scattering and reflections, which introduce noise such as speckle. Digital image processing plays a large role in noise reduction and contrast enhancement. And I also wanted to point out that there's also other methods that these techniques can be used for, such as non-destructive testing, which you can see on the right photo. So, some biomedical or medical in general applications. So, ultrasound imaging is commonly used in medicine because it's non-invasive and provides real-time visualization of internal structures. Common applications include pregnancy monitoring, organ imaging, and blood flow analysis. Digital image processing plays an important role by improving image quality through techniques such as noise reduction and contrast enhancement. These improvements allow clinicians to better interpret these images. This highlights the connection that I wish to make between engineering and medicine. The engineers develop the imaging systems and processing algorithms, while healthcare professionals use the resulting images to make clinical decisions. Advantages and limitations. So, ultrasound has several key advantages, including being non-invasive, cost-effective, and capable of real-time imaging. It is also safe because of the lack of ionizing radiation. However, there's also very important key limitations. The image quality is often degraded by noise and artifacts such as speckle, and ultrasound has limited penetration through bone and air. In addition, image quality can heavily depend on the operator of the product. Digital imaging is used to address these limitations by reducing noise, enhancing contrast, and improving visibility of important features, which leads to a much better diagnosis. Comparison with alternate approaches or alternatives. CT and MRI imaging provide high resolution and more detailed images compared to ultrasound. They allow for full body imaging and are less dependent on the operator. However, they are much more expensive, as we'll discuss later, and require longer scan times, especially an MRI scan. Instrumentation, tools, or computational framework. Ultrasound imaging include both hardware and software components that together create medical images. Transducer arrays act as sensors, transmitting and receiving acoustic signals, which are then amplified and converted from analog to digital using digital circuitry. There's also various software components such as DCOM or digital imaging and communications in medicine, which allows medical images to be stored, transmitted, and accessed across different points. Other tools like Python and MATLAB and Python are commonly used to develop and test these algorithms before they are used in everyday systems. Important algorithms include beamforming from image formation, as well as deconvolution for image recognition and image reconstruction and enhancement. So, technical aspects. Ultrasound imaging is rooted in the transmission of high-frequency sound waves into the body. These waves propagate through biological tissues and interact with them. When the waves come across boundaries between tissues with different acoustic properties, part of the wave is reflected back. The reflection depends on the differences in acoustic impedances and tissues. There's also computational principles, but we discussed those earlier, so I will skip to the next slide for sake of time. 7. Cost considerations. Ultrasound imaging is much more cost-effective than CT and MRI. Typical procedures have a range of a few $100s, as seen there, while CT and MRI scans can cost several thousands of dollars. This cost advantage comes from several factors. Ultrasound is more portable and requires less infrastructure compared to CT or MRI systems, and they also have real-time imaging, which decreases the need for scans to be done again. Furthermore, ultrasound does not use ionizing radiation, which lowers regulatory and safety-related costs. Digital image processing plays a role in this by bettering imaging techniques. The DIP decreases the need for more expensive imaging hardware. Safety and ethical considerations. Ultrasound is generally considered very safe because it does not use the ionizing radiation, making it safe for repeatable use in real-time monitoring, such as in pregnancy. However, at high intensities or long exposure times, ultrasound can produce biological effects such as tissue heating or mechanical stress. Ethical considerations are that AI and data-driven approaches can introduce biases, not have the most reliable results, or produce a misinterpretation of these results. So, future directions. One future direction is 3D and 4D ultrasound images, which provide more detailed and real-time visualization of these internal structures. These systems require significant computational power, which has led to the use of parallel processing technologies such as GPUs and FPGAs. However, challenges remain in managing the large amounts of data and achieving real-time performance. So, another one is ultrasound guide and 3D printing. Another emerging technology, like I said, is this. Recent research developments that show that ultrasound can be used to guide the structures directly into biological tissue. This represents a shift from using ultrasound only for imaging to a part of treatment and intervention. It establishes more precise and minimally invasive procedures, which is the biggest goal in medicine today. Here are my references, and that's it. Thank you.